Have you ever wanted to make super simple things incredibly complicated? Well, me too. Today we're going to take 3 crazy simple things and make them complicated by explaining the physics behind them. Let's get started. The first thing we're going to look at is something we all do every single day: walking. Not many people realize, but we couldn't walk anywhere without friction. And of course, the concepts of Newton's third law. The best way to explain the concepts of Newton's third law is to look at a free body diagram and to see it in real life. So, let's look at someone walking. Now, let's take a look at her foot right here. Here we can see the force her foot applies backwards on the ground and the equal and opposite force the ground applies forward on her foot, which moves her in the forward direction. Now, here's where things start to get a little complicated. Imagine this: the human body, as we walk, takes the shape of a pendulum, more specifically, an inverted pendulum, with our center of masses as the bob. Simple inverted pendulums exhibit simple harmonic motion if they don't fall over when they move, and typically humans don't fall over when they walk, so we can use the period equation of a pendulum in simple harmonic motion to figure out the speed it takes for our center of mass to return to its original location. Speaking of pendulums, let's examine our next action: swinging. It's pretty obvious that a swing is a pendulum, and when we look at the pendulum, we can find out many things about its motion. So, let's take a look at a swing in motion. As you can see, the swing moves forward and then moves back in the same direction, just like a pendulum does. Now, let's take a closer look at this pendulum. More specifically, let's look at the energy of the pendulum. At its highest point, the pendulum has no kinetic energy and all of its potential energy. We can see why if we look at the equations for kinetic and potential energy. At the highest point, the pendulum's velocity is 0 because it's changing directions. This gives the pendulum 0 kinetic energy. And if we look at the pendulum's lowest point, we can see it has all the kinetic energy and 0 potential energy. If we look at the equations again, we can see the pendulum has 0 potential energy because it's at its lowest point and its height is 0. Using the equation for the law of the conservation of energy, we can find the pendulum's mass, height, or velocity with a set of given variables. Since the swing is a pendulum, we can use the period equation to find the time it takes the pendulum to return to its original location. When we look at the equation, we can see that the only factor that affects period is the length of the pendulum, since the other variables are given constants. So, we know what a swing does when it's moving, but how does a person actually start swinging? Well, the answer is energy conversions. When a person lifts their legs up to swing, it raises their center of mass, which increases their potential energy that's then converted into kinetic energy when a person lowers their legs again. Finally, let's move on to the last action: rolling. First, let's focus on the energy of things that roll. It's important to know that rolling objects have translational kinetic energy and rotational kinetic energy. To see this, let's look at a basketball rolling. Here we can see the basketball has translational kinetic energy because it is moving forward through the screen. We can also see that the basketball has rotational kinetic energy because it is rotating around its own axis as it moves forward. We know the translational kinetic energy equation is Ke equals 1/2 mass times velocity squared, and we can convert this equation into the rotational kinetic energy equation, which is 1/2 I times omega squared, where the I stands for moment of inertia, or the tendency of an object to resist a change in angular velocity, and the omega stands for angular velocity, which is measured in radians per second. Moments of inertia is an important concept in rotational motion, and it is important to understand that an object's moment of inertia depends on how the object's mass is distributed and the object's center of mass. Finally, one last important piece of rotational motion is a rotating object's momentum. Translational momentum is given by P equals mass times velocity. Using the equivalent rotational variables, we can find the equation to figure an object's rotational motion. The equation is L equals I times omega, where once again, I is moment of inertia and omega is rotational velocity. Well, there you have it. Physics of the simple, with 3 incredibly basic actions made complicated by physics.